Agriculture is a significant contributor to climate change mainly through greenhouse gas emissions, including carbon dioxide, methane, and nitrous oxide. Conventional practices like synthetic fertilizer, land use change, and livestock management are major sources of the emission, impacting the biodiversity and ecosystem health. The carbon footprint of agriculture measures total emission from farm to market, impacting our climate, biodiversity, and ecosystem health. With the global demand for food rising due to population growth, the threat of agricultural system is expected to intensify, further harming the environment. However, sustainable farming practices present a promising solution. They can help reduce emissions, enhance carbon sequestration, and improve resource efficiencies. By embracing this method, we can work toward a healthy planet for future generations, like the figure below.
Since agriculture is very important in reducing carbon footprint, so how can sustainable farming practices effectively contribute to reducing the carbon footprint in the agriculture sector? And what are the main challenges that might face in adopting sustainable farming methods to minimize carbon emissions? In this video, we will talk about mainly on this problem.
There are 5 objectives of this research. Firstly, to quantify the carbon footprint of agriculture through food waste management impacts. Secondly, to assess soil conservation's role in reducing GHGs within sustainable farming. Thirdly, to identify effective waste strategies for lowering agricultural GHG emissions. Then, to evaluate the technological innovation like anaerobic digestion in maximizing GHG reduction. And lastly, to determine the most sustainable waste method in minimizing agriculture's carbon footprint.
General overview of carbon footprint in agriculture. The carbon footprint is a crucial measure of the environmental impact of farming practices, with the agriculture sector contributing approximately 18% of global greenhouse gas emissions. Greenhouse gases such as carbon dioxide, methane, and nitrous oxide have led to global emissions reaching about 54 billion tons of carbon dioxide equivalent in 2090. Food systems are responsible for around 70 billion tons of carbon dioxide equivalent, a 60% increase in 1919. As shown in Figure 1, in 2090, non-food sector made up 69% of global emissions, while agri-food systems contribute to 31%. Within that, farm-gate activity account for 30%, pre- and post-production processes from 11%, and land-use chain at 7%. This highlights the significant impact of agri-food systems on greenhouse gas emissions and the urgent need for reduction strategy. Major emission sources, so as Figure 2, include enteric fermentation in livestock and fertilizer allocation. Additionally, land use changes such as deforestation for agricultural expansion exacerbate the emission.
And then we come to the role of soil conservation in carbon sequestration. Soil plays a crucial role in carbon sequestration, and there are few ways to reduce carbon footprint. First of all is no-till or reduced-till farming. It is to prevent soil disturbance and reduces CO2 emission from organic matter decomposition and maintain stable carbon levels, and it can help to retain topsoil which are rich in organic material and increases soil organic carbon over time. Secondly, farmers can grow cover crops during off-seasons to capture CO2 through photosynthesis and add organic carbon to the soil after the decomposition. And then it can also prevent soil erosion. Thirdly is crop diversification. Different rooting depth enhance soil organic carbon at various depths and improve soil health. And it can also support biodiversity by providing habitat to beneficial insects and pollinators. And it can reduce reliance on agriculture aids, thereby decreasing CO2 emissions.
Next, we are going to discuss how organic farming and regenerative farming can reduce the greenhouse gases emission. First, the organic farming can reduce the usage of synthetic fertilizer. The organic farming can substitute the usage of synthetic fertilizer inputs with compost, manure, and nitrogen-fixing crops. This can significantly lower the synthetic fertilizer and pesticide use, and can translate to decrease the nitrous emissions, which is a potent greenhouse gas. And then it can also lowering the overall greenhouse gases emission associated with fertilizer production and application. Then the organic farming can also indirectly reduce greenhouse gases emission by minimizing tillage, which demand substantial fuel for tractor and machinery use. The reduced till or no-till practice can decrease the fuel passes and reducing fuel consumption and carbon dioxide emissions. Lastly, the regenerative farming can also reduce the greenhouse gases emission by enhance the carbon sequestration. Regenerative farming practice like no-till farming, carbon cropping, and agroforestry can reduce the soil disturbance and improve the soil carbon sequestration. This method can increase the soil stability to store carbon and turn it into a carbon sink rather than a source of carbon dioxide emission.
The introduction of Internet of Things IoT is meant to evolve the traditional agricultural technology into a modern agricultural technology which emphasizes on a data-driven powerhouse. IoT-driven smart farming practices improve the efficiency of agricultural production while reducing the environmental impacts. The advancements are obtained through precise monitoring and crop conditions controlled by the IoT technology. Farmers then are allowed to plant more efficiently. Farmers will be referring to the real-time data which guides them to make decisions on several factors that influence the production of the crops. The process of IoT in farming, data gathering, environmental factors such as temperature, humidity, and soil moisture are continuously monitored using IoT sensors. Next, data transmission. The gathered data is transmitted to a central processing unit via wireless networks. For large farmlands, LoRaWAN is ideal, while Wi-Fi is better suited for smaller, controlled environments like greenhouses. Third, data processing. The collected data is processed using cloud-based system and analytics platforms such as ThinkSpeak, AWS IoT, and Tinger.io. And lastly, application layer. The processed data is used to guide real-time actions such as adjusting irrigation schedule based on weather forecast or deploying pesticide in areas with detected pest
which
activity.
are landfill, incineration, composting, anaerobic digestion, animal feed, and donation, highlighting their verifying impacts on greenhouse gas emission. The study also notes that the effectiveness of waste management strategies is influenced by food characteristics such as energy and water content. High-energy foods yield better results with anaerobic digestion or incineration, while high-water foods benefit from composting. Landfilling generates the highest emissions, particularly for energy-dense foods like beef, which contribute significantly to climate change. Conversely, donation and anaerobic digestion are the most effective methods for reducing GHG emissions. Donation prevents edible food from being wasted, while anaerobic digestion converts waste into biogas, which can replace fossil fuels. Therefore, incorporating effective food waste management into sustainable farming not only minimizes waste but also conserves resources and lowers GHG emissions, thereby supporting a more eco-efficient agricultural system. Expanding technological innovation in sustainable agriculture is vital. Tools like precision agriculture, IoT sensors, and renewable energy can significantly lower emissions by optimizing resource use such as water, fertilizers, and fuel. For example, IoT sensors allow for a real-time monitoring of soil moisture and crop health, enabling targeted intervention that minimize chemical inputs and reduce machinery usage. Showcasing successful tech-driven farms highlight these benefits. Additionally, case studies on regenerative practices like crop rotation, cover cropping, and reduced tillage demonstrate their positive effects on carbon sequestration and soil health, emphasizing the value of diversified cropping system and soil conservation. Policies that subsidize conservation tillage, organic farming, and renewable energy are crucial for supporting farmers in adopting sustainable practices. These incentives can fund IoT monitoring system, energy-efficient machinery, and renewable installation, easing the transition from conventional methods. Implementing effective food waste management strategies such as anaerobic digestion, composting, and food donation is also essential. Anaerobic digestion reduces methane emissions and generate biogas, providing a renewable energy source that decreases reliance on fossil fuels. Lastly, investing in farmer education on sustainable practices like precision agriculture and soil health through training programs and remote sensing monitoring is vital for reducing carbon footprint and building a resilient, eco-friendly agriculture sector.
So in conclusion, we conclude that sustainable farming represents a transformative pathway toward reducing the agricultural sector's substantial carbon footprint and supporting global climate initiatives. Sustainable farming practices offer effective solutions to these challenges by focusing on carbon sequestration, reducing emissions, and improving resource efficiency. And by using real-time data to optimize resource usage, such as water and fertilizers, farmers can achieve higher productivity with lower environmental impacts. By adopting waste management strategies like anaerobic digestion and food donation, farmers can effectively divert waste from landfills and repurpose it into valuable resources such as biogas for energy or compost for soil enrichment. And lastly, these methods not only reduce greenhouse gas emissions but also ensure that farming remains viable and productive for future generations, reinforcing the sector's crucial role in achieving a sustainable, low-carbon future.